So let's start. So welcome everybody, I'm Pasquale Scarlino. Today we have a pleasure to have Jérôme Estève from the Laboratoire de Physique des Solides at QSE University. Jérôme worked on a pretty broad spectrum of quantum technology, even on cold atom in his previous time in the Laboratoire of Estève in Paris, but he's currently more focusing on microwave quantum technology, quantum optics, and conventional superconductor. And today we'll tell us more about this inelastic tunneling in impedance in microwave environment. So please, Jérôme, for it.
Thank you, Pasquale. Thank you for having me here. So today I will explain you, hopefully, what this means to have inelastic tunneling in a strange environment. And before going into the details of this, I want to try to motivate why we want to do this. Okay, you will not see the title, I guess, but okay, it doesn't matter so much. So the idea is that we want to study a broad field of physics, which is quantum electrodynamics. And as you know, quantum electrodynamics is the quantum theory of light and matter interaction. And so in this theory, there is a very important number which appears, which is called the fine structure constant. And the fine structure constant can be very easily defined from the basic interaction between two charges spaced by a distance r. And we take the typical interaction energy for these two charges, which is the first term that appears here, and we multiply this by the time for the interaction to travel between the two charges, which is the distance divided by speed of light. We get an action which we have to compare to h bar, and this is the fine structure constant. So this was introduced by Sommerfeld at the beginning of the 20th century. It was introduced mostly to understand the spectrum of hydrogen atoms, and this is why it's called the fine structure, because it gives you the fine structure of your spectral lines in the hydrogen atoms. And this number, as most of you know, has this strange value, which is 1/137, so this is small. And people have thought a lot why you get this number, and this is one of the mystery in physics. We don't know why we get this number, but so you have a lot of conjecture about this. We'll not go into that, but the fact that for us, like pragmatically, it's a small number. It's small compared to 1, which means if you do a quantum field theory, any perturbation approach you will have in your theory will be an expansion in powers of alpha, and since alpha is small, your perturbation theory will work very nicely. And so that's good for physicists, but more pragmatically also it's good for nature, because this is why atoms are stable. This is why the proton is stable, and this is why, so if alpha would be on the order of 1, the hydrogen atom would not exist. So we would not exist, nothing would exist in this universe. So it's good that it's small, and also we have some important property that light mostly decoupled from matter, which means in your atoms, basically the rate of spontaneous decay, so where your atoms de-excite itself by emitting a photon, this is small compared to the frequency of the light that is emitted. So there's a ratio which is on the order of alpha cube, and this is a very small number. So your atoms spend a lot of time before you emit the photon, and this is why sunlight goes through the sky, this is why the sky is blue, and so on. So these are all very nice features, but for us, what I would like to motivate is that it would be interesting if we could push this to a regime where alpha is on the order of 1, such that we are going to challenge our theoretical friends so that their nice perturbation expansion might fail, and see if we can learn something by building some experimental setup where we can reach a high value of alpha and still do QED and see what happens. Okay, so before going into that in more details, I want to give you a bit of history, since there are a lot of students, about the history of QED and how it exploded, because that's something that maybe some of you know, but it's not, I think it does not appear enough in the lecture. So I want to give you something, I mean the title is lamp shift. And I want to stress a bit the importance of lamp shift in the development of QED. Because actually QED was, I mean, you see like Sommerfeld introduced this notion in 1916. And actually, people say that you have citations from many physicists. Then there were 20 years where actually nothing happened. And the reason for that is that theories were blocked because they were encountering infinities everywhere in the theory. And the technique came from the discovery of Lamp shift and the calculation of Lamp shift by Bethe. So the Lamp shift is a small shift of one of the hydrogen line. Well, maybe you know or your hydrogen spectrum, but in the Dirac theory you have the two levels, which has 2p1/2 and 2s1/2, should be exactly at the same energy, because in the Dirac equation you don't have coupling to the electromagnetic field. And well, what Lamb measured, and this was just after the war, so this is in 1947, so there were huge efforts during the war to build a nice microwave source, to build a radar, and he used that to make a very precise measurement of this splitting. And this is from the PRL paper, where he got the Nobel Prize for this discovery later. So the black line show what you expect for your spectrum versus magnetic field, so you have some Zeeman shift. But you don't have to worry about the detail. Is that what you see that the data points, they don't match the solid lines, which are Dirac equation prediction. They match some other lines, which are shifted by 1,000 megacycles, so 1 gigahertz. Okay, so he presents this result at a famous conference, which is the Shelter Island Conference. And in the audience, it's crazy. You have all the people we know. You have Feynman, you have Dyson, you have von Neumann, Oppenheimer. So all the people from the Manhattan Project are here, and other people also. And then Bethe hears this talk, and he takes, during the train trip back from the conference to his lab, he makes the calculation. So if you have some time, you can, there's a nice interview of him at this. So this is a link to the video. So if you have 10 minutes to spend, you can watch him explain how he watches the talk of Lamb and how he gets the idea that he can make the calculation and how he makes the calculation during his train trip. And he gets the right result. He's not sure about the factor of 2, so when the train arrives, he runs to the library and check that his factor of 2 is right, and it was right. And so he explains the Lamp shift. You can try, take a train, you have no internet, no book, and you try to compute the Lamp shift. And then you realize that these guys were really, really impressive. I mean, and so anyway, and what the insight of Bethe is that you have to think that actually already in one of the states of the hydrogen, the electron mass is already renormalized by all vacuum fluctuation. And the other states, they're also renormalized by the same infinite terms of your expansion. But the two expansion series are slightly different. And when you make the difference of the two, then you have a finite quantity, which gives you exactly the Lamp shift. And this was very important because this was the first time someone knew how to deal with these infinities, and this triggered the full story of QED, and Finger computed the anomalous electronic moment and so on. So you have quotation from Dirac and Dyson saying that this was really a key moment in the development of QED and so in the development of modern quantum field theory. Okay, so that was, and I will show a bit of lectures later, so that's why I want to share that with you. Okay, so let's move to more humble goals and come back to what we do in the lab. As I said, we want to possibly build setups where we have QED in a strange regime, so with a high fine structure constant. And for that, there's a nice way to see that is that you can just rewrite this fine structure constant as a ratio of two impedances. So one is the impedance of electromagnetic wave propagation in your medium. So if you work in vacuum, you have the vacuum impedance, which is 377 ohm. And you divide this by the quantum of resistance, so the Franklin constant. which is 25.8 kilo ohm, and this gives you just some rewriting of the same constant I introduced before. It's just exactly the same expression expressed with different physical quantities, and you get this 1 over 137 again. But what it tells you is that if you want to engineer alpha, what you can do is engineer the impedance of the medium where your wave propagates. And that's what we're going to do in circuit theory. So we're going to build circuits, so metallic structures on the wafer where electromagnetic waves can propagate. This is going to be in the microwave regime. And this is, for example, a coplanar waveguide. So you can have a microwave signal that propagates between and this central wire, and this is your ground plane around. And you can model this, as you know, as a series of LC circuits. And the impedance of this medium is going to be given by this, the square root of the ratio between your inductance and your capacitor. So typically when you do this metallic structure, you get small impedance on the order of 50 ohm. So that's why in the lab your cable are labeled 50 ohm cable. It's to match impedance on some circuits. And what we're going to do is that actually we're going to try, so if you want to increase Z to get high alpha, so you want to reduce this capacitance and maybe increase this inductance as much as you can. Thing is that it's actually not so easy to have very small capacitors, so we're going to play mostly with this inductance here in the lab. So we're going to engineer circuits where this inductance is very large. So there are different ways of doing that. So at some point, actually, people saw that you could not do it just with metals. It happened that it's not true. You can do it with just metallic circuits. If you, for example, you do some very fine winding of a coil, then you will build some medium with an effective impedance which can be very high. So there's a breakdown in Saclay and also in Vienna. And then there's another way where you say, well, I'm going to keep my geometry as just a line where microwave signal can propagate, and I'm going to use a metamaterial where this inductance per unit length of the line is going to be much higher than for a bare metal. And again, there are two approaches to do that. The first one is to use what's called chains of Josephson junction. So this is what Pasquale is doing, for example, and also Vladimir Maluchayan is doing here also at EPFL, and many other people are doing that in the world. And you have a second approach, which is to use a strange material. Instead of a metal, you're going to use what's called a disordered superconductor, and I'm not going to explain why, but in this disordered superconductor, you get no propagation loss, so it's a superconductor, so it's perfect conductor for current. There's no dissipation, but still you have a huge inductance due to the energy, to the kinetic energy of the Cooper pair that carries the current in the line. So there are a lot of possible materials. So you have some alloys, and you also have what's called granular aluminum, which is aluminum with a bit of oxygen, so that you get grains that form in the metal. And this introduces disorder, and such gives you a high inductance at the end. So this is useful for many applications. For example, you can build better qubit, better fluxonium qubit, and you can do this using this type of system. And also, this is useful for many applications in quantum computing science, quantum science. And I want to show you what we can do with this material and fundamental physics. So the idea I want to, so the device I want to look at is a simple device where we will have a conductor. So this box here is going to be a basic quantum conductor, which is a tunnel junction. So a tunnel junction is an object where you have two electrodes, two metallic electrodes, which are separated by a thin insulating layers, and a charge can tunnel from one electrode to the other if you apply a voltage on the junction. And the idea is that, okay, so this is a very basic circuit. I have some DC power supply, I have a conductor, I have electrons going through. And basically, if you don't do something special, you will just see some kind of Ohm's law where the current will be proportional to the voltage with some tunnel resistance that appears here in the junction. And what we're going to add is that in the middle of the circuit, we're going to add a piece of this high impedance medium, so a piece of medium where the fine structure constant is large. And this can change everything for the following reason. So here you have to bear with me a bit with the calculation. So the idea is that the voltage that the electron will see before they turn on the junction, or the voltage that will drive the electrons through the junction, is going to be the sum of this DC voltage you apply, plus some quantum voltage that is due to the electromagnetic field fluctuation that I see that appear here at the end of this high impedance medium. So if you have to solve this problem, you know how to do it. You have to first find the eigenmode of the system, classically. So there's a piece of line, so you know that you have a standing wave pattern that appear in this line. You put the right boundary condition, and this will give you some normal modes, which here I draw some the first one. So you have some quarter wavelength mode, then you have a 3/4 wavelength, and so on. And this mode you will quantify, and you will have some quantum destruction and annihilation operators that will appear. So this commute with unity. So they create boson and annihilate boson. And in front of that, you will have something to give the right dimension. So you will have, here I'm considering an operator, which is called the flux. I guess we don't know that, but the flux is related to the derivative of it's the integral of the voltage. And this is the natural way to quantify an electric circuit, is to use charge and flux. So this flux is proportional to this flux quantum. This is a constant of nature. Then some bosonic operator, like you will have in a harmonic oscillator, your position will be L plus A dagger, and then you have some dimensionless number that appears. And this is where the greatness, well, the importance of this dimensionless constant is going to govern if you're in a weak alpha regime or in a strong alpha regime. So if you have weak vacuum fluctuation, strong vacuum fluctuation. So this number is directly proportional to the impedance of your line, and so to the fine structure constant of the electromagnetic world that lives in this piece of material. So if you have if alpha is small, this number are small, it means your vacuum fluctuation are small compared to the quantum of flux. So they will have a minor effect on your transport. But if you can reach a regime where this effective fine structure constant is very high, then this number will be high, which means this vacuum fluctuation will be very strong, and they will affect your transport a lot. So why is that? Maybe we're going to accept this for the moment. So the idea, so I prepared the calculation, but I'm going to skip it, I think. The idea is that, you can get to the result maybe in an intuitive way by saying that, so your electron will tunnel through the junction, and this tunnel in turn you can write as some, you destroy one electron and one electrode and create it on the other side with some tunneling amplitude, TKQ. And the idea is that, when your electron tunnels through the junction, it also has to tunnel through the environment. So you conserve the charge. So if you have one electron that tunnels at the junction, it also goes through the full circuit, including your piece of circuit which has a high impedance. This means you are translating the charge degree of freedom of these modes by one electron. And you know in quantum mechanics that to generate this translation, you have to take the exponential of the operator conjugate to the charge, which is the flux. You multiply this by the amount of your translation, which is here one electron, and you divide by h bar over 2. So this you get this translation. This tells you that actually your tunneling operator, this harmonic operators, they get dressed by a translation operator, which is going to be proportional to this A and A dagger operator with this coefficient that I just defined, which actually encodes how strong is your fine structure constant in your medium. Okay, and this, again, that's what we see. So if lambda is small, then I can forget about this exponential. It's going to be the identity, and my tunneling remains the same. But now if lambda is very big, you see that I cannot neglect this translation here of the mode, and something will happen. Okay, so we can do the experiment. And that's how we do it in our team. So this has been done by many other people, so I will just show you how we do it in our team. But you have to keep in mind that a lot of people have been doing that for a very long time. And just for us, we are going to use a simple design, which is the following. So this, we're going to have a piece of metal, which is granular aluminum, which has the size I show here. And this is the piece of medium where the effective electrodynamics happens with a high fine structure constant, because the impedance, characteristic impedance of the line is large, between 5 to 6 kilo ohm. And if you take the formula I gave you before, this gets you to a world where the fine structure constant is on the order of 0.1. So about 1 order of magnitude larger than in a vacuum. And then at the end of this piece of high impedance medium, we put a small tunnel junction, which is what you see here with e-beam imaging. So you barely see here. It's a very small object where you have two electrodes separated by a thin oxide layer. So you have the two electrodes are these two fingers that cross here. So the junction is just a small square at the intersection of the two wires here. And then this is connected to the rest of the world through a 50 ohm line, which is made of aluminum, which is this pad here. And this enormous pad here is just the ground plate that you see here in the circuit. Okay, and what we can do in this setup, we can DC bias. The setup measures the current that goes through these conducting wires and the junction at the end. And we can also send microwave signal through a circulator and get back the reflected signal from our high impedance medium. And okay, so what do we see when we measure the current through the junction? Okay, one important thing that I completely forgot to say is that this junction is a superconducting isolator, superconducting junction. So it means that the density of state in the two junctions is gapped by the superconducting gap. So it looks like this. So there is a Fermi level here is in the middle of these two peaked density of state. The opening here is the gap, and so you feel half the levels below the Fermi level, and this gives you this picture for the density of occupied level for your electron. So if you have no environment, what you expect is that if your two density of state are shifted by less than twice the gap, there's no current, because basically your occupied level are facing the gap, so the electrons cannot go through. There's no empty state on the other side. And as soon as you reach twice the gap, then you align this first occupied level to the first unoccupied level, and you have current that flows through the junction. So what you should see, or what you see if you do the experiment without the high impedance environment, you see an IV curve which has a sharp jump at 2 delta, and then you have basically a linear current that grows because you have more and more state available to flow in. Okay, and what we immediately see is that we have these steps that appear on the IV, and these steps are signatures of the fact that the electron tunneling is very much affected by the presence of the electromagnetic modes that are present in the circuit. So the different curves here, they correspond to different temperatures. And so you see two effects. You see first that there are steps below the gap, and there are also steps above the gap. So what are the physical processes that are happening here? So let's start by looking at what happens above the gap, because that's maybe easier to understand. So above the gap, what is happening is that first, just above the gap, you have a strong reduction of the current compared to what you would get without the environment. So this is the formula that is written up there, because what you're trying to do is you're trying to have an electron that tunnels through your medium, and this electron has just the energy to cross the gap, so it cannot give its energy anymore to any other photon. So basically you want to have the electron that tunnels and keep the environment in vacuum. So for that you can evaluate this matrix element. It's very easy. So it's this, you have vacuum on two sides, you don't change the environment, but you apply this translation operator, which corresponds to moving your charge. And this you can very easily evaluate, and this gives you an exponential reduction of your current with what appears in the exponential is actually this file structure constant that we discussed before. So if your lambda is large, this factor can be small, very small, and you're going to reduce a lot the current that flows through the junction at this voltage. Okay, what happens then is that at some point, if you increase the voltage, your electron will have enough energy to actually tunnel, and the remaining energy will be transformed into a photon. So this is depicted here. So you have you're above the gap, so your electron could come in, and it has actually above the gap plus h bar omega. So it means it can tunnel and emit a photon into the environment, and so it gives you a new tunneling process, and that's why you get an increase of the current in a step-like manner. And actually below the gap you have the same type of process, but the other way around. Now your electron can tunnel by absorbing a photon to get the missing energy to climb up the gap. And this is what happened here. So you're below the gap, but you can still tunnel by absorbing a photon. And of course, this cannot happen at 0 temperature. There's no photon available, so this will only happen when you have enough temperature, enough thermal occupation of your mode to have such that these processes are possible. So this is a zoom here of what happens below the gap and this actually gives you so I should have put a conversion of this into mean photon number. So you can do this at home. I mean, this is a 6 gigahertz mode. You know your Bose-Einstein formula. So you can convert this temperature into a photon occupation, and we will see that we can see actually very small amounts of photons. So this should be about, the first curve, like the green curve, is going to be about 0.1 photon on average in the mode. Okay? So this is an example of how the current, how the way that the current can flow through a circuit can be very much modified by the QED around this conductor. Okay, so we can actually, again, just to say, I mean, this has been done, so this, I think, started maybe in the 80s or the 90s, and we're revisiting these effects, and one thing that we're done at this time is that we can look actually at what's happening to the photons that are created in the environment. This is what I will show on this curve. So now I just, so basically it's the same experiment as before. It's the same run, but now we look at this microwave signal that comes out from the environment, and we see these curves. And again, what we see is that actually, so let's look at the curve at first at very low temperature. We see that nothing happens, and that above the gap, but not at the gap. I mean, you see that here you have a current that starts flowing at 400 microvolts, which is twice the gap. And here we see photons arriving at 420 microvolts. So this is in agreement with the fact that this step corresponds to the beginning of photon emission because before your electron has not enough energy. So we see a first step at 420 microvolts, and then we see many steps which corresponds to the fact that you create 2 photons per tunneling process, 3 photons, and so on. And again, if you have some thermal background, below the gap, we see actually that the population in the resonator go down because the junction is absorbing photons so that electron can turn on through the junction. Okay, so one question you can, so actually you can think about the junction as, so now you're doing some kind of thermodynamics where your microwave modes are connected on one side to thermal environment, so you have Rosenstein on one side, and the other side you have this tunnel junction, which is a strange object that can either cool the modes by absorbing photons, or heat the mode by creating photons. And what we were wondering is that what happens at this, at some precise voltage where you actually have a balance of heating and cooling. And we were surprised that we're going to look right here, where you see that on average, I have the same signal in my cavities and at very low bias where nothing happens. This is a line here. And this happens close to the first step of emission. And what we saw is that actually what's strange is that, so when you're slightly below this value, you get a dip because you are absorbing more than you emit. If you're above, you have a peak, you're emitting more than you absorb. And what was surprising is that in the middle, you don't get a flat line, you get this double-shaped curve, and this was very intriguing. So usually if you try to make thermodynamics with something that absorbs and cool down, you expect something flat, and this is not flat. And so basically you're not changing the mean energy of your system, but you're changing its entropy because you're redistributing between your high and low frequency components because of the junction. So if I have time, I mean, you can think about why this is happening and see if you get the answer at the end of the talk. Okay. So once we know what's, so we can look at the effect of the junction on this mode in another way. So now I'm going to go down to 0 temperature. So I'm going to start with an empty resonator. There is no thermal occupation, so I'm at 20 millikelvin. So I'm in vacuum for my microwave modes. And we're going to probe the mode by sending a tone, which is a red arrow coming on the system, and we're going to look at the reflection, what comes out with a vectorial network analyzer. Okay, and again, we're going to bias the junction at different voltage, see what's happening. And this, so here one vertical line gives you the spectrum that we observe in reflection. And we see that there's a dip at a precise frequency which corresponds to the frequency of the fundamental mode of my quarter wavelength resonator. So way below the gap, not much happened. I just see my resonance, and we look at how this resonance gets modified when we get close to the gap where we have this photon exchange due to the tunneling of electron. And we see this series of discontinuities in the spectrum. So every time we cross the value which, starting from the gap, decreases by h bar omega over e, then there's a new possible absorption channel for the system. So here I can absorb one photon. So I can have one photon absorption and electron tunnel. So this actually, this is such a big effect that my resonator disappears because the microwave are too absorbed. So I don't see my resonance anymore. In this region, I can only absorb photons 2 by 2. So I still have some signal. Here I absorb them 2 by 2, 3 by 3, or more. In here, 4 by 4. Okay. And every time you have this new channel that opens, you see a broadening because you have more losses. And you also see a shift of the resonance. So that's the picture we have. So this level, I mean this So your mode is like an harmonic oscillator, so I can draw the levels here, which are the Fock states that describe my system. So there's a ground state at the bottom. The first state corresponds to one photon in the mode, and so on. So in this regime, already the first photon state is not stable because it will be absorbed by electrons that turn out. Here the electrons, they need to absorb at least 2 photons to go through the barrier. So this is why the first Fock state with the 1 photon is not affected by the tunnel junction, and so on. So actually I can shape my system such that my losses keep some state not touched and just affect the other states from some given photon number in the system. And this is a huge effect because actually in this regime, of course you always have some remnant 1 photon loss in your system, but in this band of voltage here I have my 2 photon losses are actually 25 times the 1 photon loss, so it's an effect we can clearly measure. Okay, and there's a funny effect that appears, which is called quantum Zeno effect, or quantum Zeno dynamics, which is that actually if you manage to isolate, so you have a quantum system and you manage to cut your Hilbert space in 2, so you draw a boundary in the Hilbert space such that on one side of the boundary you have small losses, and on the other side you have strong losses. Actually what's going to happen is you're going to confine the dynamics in one part, so like your quantum state will remain on one side of the boundary. You will not want to cross this boundary. And you will effectively generate some coherent evolution, even though you have a huge losses. In principle, if this broadening is infinitely large, then you can perfectly confine a dynamic to this 2-level system. And because if your system would cross the boundary, then well, you're looking at it, the environment is looking at it, so it's forbidden by the Zeno effect. So actually, you don't cross the boundary at the end, you remain confined. And this is what we measured in the bit in the experiment. So we are.
Can I ask you about this?
Yes.
What if I have a superposition state 0 and 1?
Yeah, it remains. It's
so it would not destroy.
No, it does not destroy. No. But it's fully coherent in the large loss limit. It's fully coherent.
It sounds a bit counterintuitive, because imagine I make a superposition state, and then.
So Arosh did it, and they showed. I mean, they could have a very nice control.
And I just have a process where I go, let's say, from state 1 somewhere up and
but
back
this process
down.
never happens actually at the end.
Why not?
Yeah, you can. It's blocked by the Zeno effect.
So it's not driven, right? It's just like I have very lossy higher states and 2 not so lossy lower states.
Yeah.
And I add a
basically, you're measuring your system all the time, so you project back.
Ah, okay. So the measurement is on.
Yeah, but measurement is the same as loss.
I mean, because if I have like a very lossy state in an atom and a finite temperature, right, you can just get excited to those states, and that kills the phase. So that's
sure, but the thing is that you need 2 stable states or even more actually. You need a clear boundary between states which are very stable and states which are not stable, and then you will actually engineer some coherent evolution in your part of the Hilbert space which is not lossy. And usually it doesn't work very well. It doesn't work very well because the scaling that you get to really confine are a bit crazy, so it's really hard. You really have to, you need a difference of the loss rate which is really enormous to get decent coherence in your system. So it's at the end practically it's not very interesting.
I see.
So we tried a bit. So the idea is that we're going to drive the cavity with a pump. So we change the amplitude of the pump, and of course, if you try if you have a normal harmonic oscillator, if you pump higher, you get more photons in your system, and with a linear relation. Okay, this is the green point and the first line at the beginning. And well, if you reduce to a 2-level system, you know that there's saturation in a 2-level system. So if you drive an atom, the more you can do is you can have a half population in the excited state, half in the ground state. So you see this saturation. And if you would have an ideal two-level system, you expect this curve here. It's not saturating because, well, I don't want to go into the details. And the experiment are the blue points. So we see a saturation that happens at a level which is much lower than here, but then it breaks down. So you start leaking into the wrong side of the boundary. So the boundary is not that strict in this region. But still, what is nice is that, I mean, in this range, mostly you have 2 photon loss, which can be interesting, like for people like Alice and Bob, like where they want to engineer 2 photon loss in their system. That's they're a bit thinking about if they could use that or not. I think they won't, but they're thinking about it anyway. Okay, so now let's come to the lamp shift. I mean, I was telling you in the introduction how nice was the lamp shift. So we also observe a lamp shift. And the lamp shift is the shift that we see in the spectroscopy here. So a lamp shift happens in a modern, the modern interpretation of a lamp shift is that every time you have your quantum system that you couple to some environment, of course the environment is going to absorb the energy, that's the first effect you see. But as soon as your absorption kicks in, there must be a shift also of the frequency of your quantum system that is coupled to the mass. And I mean, classical physics, this is called Kramers-Kronig relation, and it also applies in quantum mechanics. So your loss and your lamp shift are related. It's just a real and imaginary function of real and imaginary part of some correlation function of your environment, of your mass. And this is why we see shift here. So every time the voltage crosses the line here, there's a new process that happens. So when we cross, of course, vacuum is always stable. When we cross this line, it's the first Fock state becomes unstable. Here's the second Fock state that becomes unstable. So at the same point that the Fock state widen, because of Kramers-Kronig, they also have to shift a lot in their energy. And this is very analog to the lamp shift. And this is what we see here. So we can measure this more precisely. This is what we did. So compared to before, I just weakened my probe by a lot. And I do best spectroscopy, so I can probe the 0 to 1 transition. And I can also probe the 1 to 2 transition by doing two-tone spectroscopy. And I get these curves here. And okay, so now I told you that, well, can we push? So this curve I can predict from my QED theory, and now I have to make some QED theory with a high alpha constant on the order of 0.1, so I get some perturbation, expansion, so some nice series with powers of the fine structure constant. And this is still well under control, so we're still not enough in the regime of high alpha such that this perturbation will completely fail. So as you see, I mean, we have a very good agreement between what the model predicts and the experiment, so we can fully predict the shifts. So we have to go deeper in high alpha regime if we want to have some breakdown of this kind of expression. Okay. So I will go on a bit. So I mean, this we can observe some other phenomena in the same system. So we can now go to a much lower voltage. So we are going to. We were working close to the superconducting gap. So we're going now to move close to zero bias. And as you know, if you have a superconducting junction at zero voltage, in principle well, it's not in principle, you can have a supercurrent that flows through the junction due to the Josephson effect. And we're going to look at how the fact that there's a high impedance medium is going to affect this Josephson current through the junction. So I will just skip the math. Now you have a nice Hamiltonian, which looks like before. Just now your translation operator directly applies as a nice coherent term in your Hamiltonian. And also the good thing is that since it's Cooper pairs that tunnel and not electron anymore, your effective quantum of resistance is 4 times smaller. So it's much easier to get, it's easier to get high alpha with quantum, with Cooper pairs than just one electron tunnel. Okay, so again, people have been doing that quite a lot in the past, especially in the quantronics group where they have studied this extensively. So what you see, like instead of step in the IV, now you see peaks in the IV, because what you see that every time your condensate level are spaced by a multiple of H bar omega, you can have a process where you Cooper pair tunnels from one condensate to the other condensate by emitting some number of photons, and so the resonance condition gives you these peaks that appears in the current as a function of voltage. And now you see we're close to zero bias. These are very small voltage compared to the gap. And what is nice is that you can actually show that these processes correspond to the emission of 1, 2, 3, 4, 5 photons exactly, if you're in the right regime. And this is what people, so they have measured the correlation function of the emitted photons, and they could actually show that indeed you have a non-classical statistic where photons come 3 by 3 or 2 by 2, and so on. Okay, and so now we did that also in our, we looked at what's happening in our sample, and we got this very strange behavior that has been puzzling us for quite some time. We obtained a forest of peaks as a function of voltage. So actually, before I was showing you just a part like somewhere here, 400 microvolts above the gap, but you see that we have these peaks that appear almost everywhere below, that was hiding before. And all these peaks correspond to inelastic Cooper pair tunneling. And they're very equidistant, the height is changing in a weird way. And actually what we see that also at the same time we have strong emission of photons in the first mode of the system. So at the lowest energy mode, I only look at 60 at the first basically resonant mode in my system, and I see a lot of emission even at voltages which are much, much larger than the frequency of where I look at. So we were wondering, is this, okay, and this is a zoom at low voltage. Just to show that actually the maximum of current is slightly shifted compared to the maximum of emission. So it points out in the direction that actually you have multimode physics appearing, because otherwise your maximum of emission would match perfectly the maximum of current if you would collect all the photons that are emitted by the system. Okay, so we were wondering, this could be really nice because this is one of the things that people would like to see in a high alpha medium, is that actually when you do your, you want to compute the current through the system, so you're going to do some perturbation theory on your translation operator. So what will appear is the correlator like this of your translation of the charge at 2 different times. And this was computed long time ago, and this gives you some spec. If you take the Fourier transform of this, you get a broad spectrum as soon as this lambda constant is large. So when lambda is small, which is the standard regime, you get something very peaked around your voltage. Basically, what I'm saying is that I will mostly emit photons such that their energy is equal to 2eV, the energy of the pair. But as soon as I move to high lambda, to high fine structure constant, then I can emit a stream of photons such that the sum of their energy is equal to 2eV, but I can have all possible colors. And for very large lambda, I will have an excess of low energy photons and very few photons at the energy of my pair. So you can picture it like this: you have all possible colors, and there's so much to 2eV. And this happens when alpha is very big compared to 1. So this could, this would be nice to see. Actually, this is not what we're seeing. And because, okay, so this happens this is independent of the resistance of the junction. Basically, this is really a property of your medium, is that as you start to inject some energy and it will break down in multiple photons of lower energy. And this is not what we see, because we built another device where we could actually vary the effective resistance of the junction. So we use a squid, so you can vary the Josephson energy in the system. And this is what we observe. So I think I'm going to go a bit fast on that, but the main idea is that I'm going to look at the emission and also at the current through the junction as a function of this Josephson coupling. And what I showed you before are curves like this green curve, where you have this crazy amount of peaks, but they actually happen for large Josephson energy. And when we reduce the Josephson energy a lot, we recover that we have only a few peaks that appear at small voltage. So actually the fact that we see this forest of peak is not just due to this nice property of your high impedance medium, it's also some very nonlinear effect that appears only at large EJ. Basically you start to put photon in the mode, so you have some non-equilibrium population that build up, and this explains why you get this large forest of peaks everywhere. So still what we can see that was nice, that this is a zoom at low voltage. So every line here is spaced by h bar omega. So you see we see the one photon process, 2, 3, 4, 5, and so on. And you see that when we increase EJ, we start to have peaks that appear in between the peaks. So which means we see higher order terms, where actually you have two pairs that tunnels and give some photon. So these are the tiny peaks here that go in between the main peaks. And so if we follow the height of these peaks, we can clearly show that it's a higher order, because you have a succession of dependence with the coupling, which is either more linear or more quadratic. So you see there's a quadratic, linear, which tells you that all these quadratic peaks, so every second peak, which was a small peak before, is quadratic, so it's a higher order term than the linear peak that appeared as integer of your frequency of your first mode. Okay, so this is getting a bit technical, so I just want to say that actually at very high energy, what you see as a threshold behavior, so it looks like it's a laser. So this also points in the direction that what is happening is non-trivial, nonlinear physics of your junction. Just to say that, well, when we have been sitting on this data for quite some time, but then the Grenoble group showed us very similar data. So we have to work with them, see what we can do. So these were the data from us. So they have a similar system, but with much more modes, so they have less finite size effect. But if we smooth our data to remove finite size effect, we have some structures that look a lot like them. So we were wondering if there are some universal behavior to understand or not. We can a bit understand what's happening with quantum optics, like truncated linear approximation. So we understand what's happening, but we don't deeply understand why we have so many peaks. So this is one first question. Okay, so I think I will. Yeah, it's time to stop. So I want